Ah, the universe. It's a place of constant motion. Stars swirl in galaxies, planets orbit their suns and moons circle planets. Even here on Earth, everything is moving. Cars drive on roads, people walk down streets, and the wind blows leaves from trees. This motion is fundamental to everything we observe and experience. To understand this motion, scientists use special concepts. One of the most important concepts is called momentum. Think of it as the quantity of motion an object possesses. It's not just about how fast something is moving, but also how much stuff, or mass, is moving. It's a simple idea, yet profoundly powerful in explaining how the universe works, from the smallest particles to the largest celestial bodies. Another key idea we will explore is impulse. Imagine you want to change an object's motion. You need to give it a push or a pull. This push or pull, applied over a period of time, is what we call impulse. Impulse is the reason why a gentle, long push can move a heavy object. It's also why a quick, sharp impact can cause a dramatic change in speed or direction. Understanding impulse helps us understand how forces interact with objects to alter their state of motion. So what exactly is momentum? In physics, momentum is a way to measure how much motion an object has. It's not just about speed. A tiny bee flying very fast might seem to have a lot of motion, but a massive truck moving slowly also has a great deal of motion. Momentum takes both an object's mass and its velocity into account. The more mass an object has, the more momentum it will have if it's moving. Similarly, the faster an object is moving, the more momentum it will possess, assuming its mass stays the same. It's a vector quantity, meaning it has both magnitude, how much, and direction. The symbol for momentum is usually the letter P. The formula to calculate momentum is beautifully simple. P equals m times v. Here, m stands for the mass of the object, typically measured in kilograms, and v stands for the velocity of the object, measured in meters per second. Let's put this idea of momentum into practice with some numbers. Calculating momentum is straightforward once you know the mass and velocity of an object. Remember our formula P equals m times v. Let's imagine a common scenario. Consider a bowling ball with a mass of 6 kilograms. If this bowling ball is rolling down the lane at a velocity of 5 meters per second, what is its momentum? We simply multiply the mass by the velocity. So, the momentum, P, would be 6 kilograms multiplied by 5 meters per second, which equals 30 kilogram meters per second. That's the quantity of motion the bowling ball possesses as it heads towards the pins. Now, let's consider a much smaller object, perhaps a baseball. A typical baseball has a mass of about 0.145 kilograms. If a pitcher throws this baseball at a velocity of 40 meters per second, which is quite fast, we can calculate its momentum. Again, using P equals m times v, we multiply 0.145 kilograms by 40 meters per second. This gives us a momentum of 5.8 kilogram meters per second. Now that we have a good understanding of momentum, let's talk about what causes momentum to change. An object's momentum won't change all by itself. If an object is moving with a certain momentum, it will keep that momentum unless something acts on it. That something is what we call an impulse. Impulse is defined as the product of the average force applied to an object and the time interval over which that force is applied. So if you apply a force for a certain amount of time, you are delivering an impulse to the object. This impulse is what causes the object's momentum to either increase, decrease, or change direction. The formula for impulse is typically represented as J equals F times delta T. Here, J stands for impulse. F represents the average force applied, usually measured in newtons, and delta T represents the time interval during which the force acts, measured in seconds. So, the units for impulse are Newton seconds. Section 5. Calculating impulse. Measuring the impact of force. Calculating impulse is just as straightforward as calculating momentum, provided you know the average force and the duration for which it acts. We use the formula J equals F times dtan. Let's explore a few examples to see how this works in practice. Imagine a golfer hitting a golf ball. The club exerts a large average force on the ball, say 2,000 newtons. This force is applied for a very short time, perhaps only 0.001 seconds, or 1 millisecond. To find the impulse delivered to the golf ball, we multiply these two values. J equals 2,000 newtons times 0.001 seconds. This gives us an impulse of 2 newton seconds. Consider another scenario, pushing a stalled car. You might not be able to exert a massive force like a golf club, but you can push for a longer time. Suppose you and a friend push a car with a combined average force of 500 newtons for a period of 10 seconds. Section 6. The fundamental link, the impulse-momentum theorem. We've talked about momentum, which is mass times velocity, and impulse, which is force times the change in time, as separate concepts. But the real magic happens when we see how they are connected. This connection is described by one of the most important principles in physics, the impulse-momentum theorem. This theorem states that the impulse applied to an object is equal to the change in that object's momentum. It's a direct bridge between the cause, impulse, and the effect, change in momentum. It's not just a neat idea. It's derived directly from Newton's second law of motion. Mathematically, the impulse-momentum theorem can be written as force times change in time equals change in momentum. Here, delta P represents the change in momentum. Remember, delta in physics almost always means change in. Section 7. Keeping things balanced. The law of conservation of momentum. Beyond the relationship between impulse and the change in momentum for a single object, there's another incredibly powerful principle that governs interactions between multiple objects, the law of conservation of momentum. This law states that, in an isolated system, meaning a system where no external forces are acting, the total momentum of the system remains constant. In simpler terms, momentum can be transferred between objects in a system, but the total amount of momentum before an interaction, like a collision, is equal to the total amount of momentum after the interaction. Momentum isn't lost, it's just redistributed. Imagine two billiard balls on a frictionless table. This system of two balls can be considered isolated because the main forces acting, like gravity and the upward push of the table, cancel each other out, and we ignore air resistance and friction with the table. If one ball is moving and hits the stationary second ball, momentum will be transferred from the first ball to the second. The first ball might slow down or even stop, while the second ball will start moving. However, if you were to calculate the total momentum of both balls added together before the collision, and then again after the collision, you would find that these two totals are exactly the same. Section 8. Cosmic crashes and billiard balls, momentum in collisions. The law of conservation of momentum truly shines when we apply it to analyze collisions. Collisions are everywhere. From the microscopic scale of atoms bumping into each other to everyday experiences like cars colliding, to the grand cosmic scale of asteroids hitting planets or galaxies merging. In any collision occurring in an isolated system, the total momentum of the objects involved before the collision is equal to the total momentum of the objects after the collision. This principle allows us to predict the outcomes of collisions, such as the velocities of objects after they impact each other. Let's consider a simple example. Two carts on a frictionless track. Suppose cart A with mass m_a is moving with velocity v_ai towards a stationary cart B, with mass m_b, so initial velocity of cart B is 0. The total initial momentum of the system is initial momentum equals mass of cart A times initial velocity of cart A plus mass of cart B times 0, which equals mass of cart A times initial velocity of cart A. After they collide, they might stick together, which is an inelastic collision, or bounce off each other, which is an elastic or partially elastic collision. If they stick together, they move as a single object with a combined mass of cart A plus mass of cart B, and a final velocity v_f. Section 9. Momentum and impulse in our world. From safety to space travel. The concepts of momentum and impulse are not just for physics classrooms, they are woven into the fabric of our everyday lives and technological advancements. Think about vehicle safety. Airbags and crumple zones in cars are designed using the principles of impulse and momentum. During a collision, a car's momentum changes very rapidly. An airbag increases the time over which the passenger's momentum changes as they come to a stop. According to the impulse-momentum theorem, if the change in time is increased, the average force exerted on the passenger is reduced, minimizing injury. Crumple zones work similarly, extending the duration of the car's impact. In the world of sports, understanding momentum and impulse is crucial for performance. A tennis player follows through with their swing to maximize the contact time with the ball, thereby delivering a larger impulse and giving the ball greater momentum and thus speed.